produced, which are ionizing because of their strong interaction with the electrons in matter. Neutrons can also interact with other atomic nuclei, and depending on the neutron's velocity, produce either fast or slow neutrons that produce radioactive nuclei, which ionize as they decay. Radiation is ionizing because as it moves through matter, it knocks electrons out of their orbits to form ions. Ionizing radiation uses some of its energy each time it creates a new ion and eventually uses up all of its energy and no longer can cause damage. Alpha particles are the nuclei of helium. Beta particles are rapidly moving electrons or positrons, and gamma rays are electromagnetic radiation of high frequency. Alpha and beta particles can often be stopped by a piece of paper or a sheet of aluminum respectively. They cause most damage when they are emitted inside the body. Gamma rays are less ionizing than either alpha or beta particles, but protection against gamma rays requires thicker shielding. The damage they produce is similar to that caused by X-rays and includes burns and also cancers through mutation. Ionizing radiation can affect living things by altering the cells that make up the living organism. Cells are made up of molecules. Cell damage is caused by interaction of radiation with these molecules forming ions. Radiation effects on cells are random. That is, the same type and amount of radiation could strike the same cell many times and have a different effect, including no effect each time. However, in general, the more radiation that strikes the cell, the greater the chance of an effect occurring. If radiation does not reach the living organism, it has no chance of affecting that organism. Methods of protecting people from radiation focus on reducing the amount of radiation that reaches the individual. The three factors that determine how much radiation reaches a person are time, distance, and shielding. The dose of radiation a person receives depends on how long the person is near the radiation source. The shorter the time spent near the source, the smaller the dose. Radiation protection procedures are designed to keep the time people spend near a source of radiation as short as possible. Similarly, the radiation dose a person receives depends on how close the person is to the source. The greater the distance between the person and the source of radiation, the smaller the dose. The dose decreases with the square of the distance. One way to minimize the amount of radiation that reaches people is to put some material called shielding between the radiation source and the individual. When the radiation strikes the shielding, it begins to create ions in the shield. Each time an ion is created, the radiation uses some of its energy. If the shield is thick enough, the radiation will use up all of its energy before it gets through the shield. Any material provides shielding, but common shielding materials are steel, iron, concrete, lead, and soil. The shielding ability of a material is measured by determining the thickness of the material required to absorb half of the radiation from a given source. This thickness of the material is called the half thickness. Radiation that has passed through one half thickness will be reduced by half again if it passes through another half thickness. The half thickness depends on both the characteristics of the shielding material and the type and energy of the radiation being emitted. Some common shielding materials and their half thicknesses for high energy gamma rays are 3.6 inches for packed soil, 2.4 inches for concrete, 0.4 inches for lead, 0.08 inches for depleted uranium, and 500 feet for air. Nuclear waste in a bitumen formation will be separated from the biosphere by hundreds of meters of rock, which is an excellent shielding material. Furthermore, radioactive waste is a ceramic and will be contained within a conventional oil well